Hi, my name is Meghna Pal. I'm 14 years old and I'm a 9th grader at Acellas Academy. For my science fair project, I've chosen the topic Insulators' Impact on the Process of Ice Melting. My research question is, how does the varying thermal resistance of different insulators impact the rate of ice melting? Now, I'm going to be very honest here. This was a 1 a.m. thought of mine because I didn't plan on choosing this particular topic for my science fair. So I think probably most people have had this thought on how to slow down the process of ice melting. But then I decided that can this have a real life impact? So it actually does have a real life impact. So preserving ice in a cost-effective way ensures temperature-sensitive treatments through cold chain techniques in preserving vaccines, insulin, and antibiotics. So especially in areas where there is poverty, using these cost-effective insulators can help save lives. So anyways, let's dive deep into my research. So first, a little bit of background information. What is ice? Sounds like a silly question, but it's actually important to know what it is exactly. So when water is frozen at or below 0 degrees Celsius, which is 32 degrees Fahrenheit or 273.15 Kelvin, it turns into a solid state. This is known as ice. Ice is considered a mineral as it is a naturally occurring crystalline inorganic solid with an ordered structure. What is the melting point of ice? 0 degrees Celsius, which is again 32 degrees Fahrenheit at 1 atmospheric pressure. ATM, 1 ATM. So this is the temperature at which ice, which is a solid, turns into water, which is a liquid. How does ice exactly melt? As the ice is heated, the molecular motion increases. Gradually, the motion overcomes the molecular attraction, which results in the ice melting and becoming a liquid. Now, I have chosen 3 thermal insulators for my project, so a little background on them. But first, let's recap on what an insulator is. An insulator is a material that does not conduct or transfer energy well. So the 3 thermal insulators I have chosen are bubble wrap, felt, and sawdust. So as everyone knows, bubble wrap, its structure consists of tiny air-filled pockets, and these pockets create a barrier that hinders heat transfer. The trapped air acts as an insulating layer, which prevents heat from escaping or entering a space. Felt, it's a type of matted fabric that consists of textile fibers condensed and pressed together. Felt acts as a natural insulator. It catches air and can capture much air. Sawdust, it's basically powdery particles of wood which is produced by sawing. So when sawdust becomes moist, it clumps together and forms an impermeable barrier that does not allow air or heat to pass through. Now, a little bit on thermal conductivity. So what is thermal conductivity exactly? First of all, it is measured in watts per meter Kelvin. Thermal conductivity shows how easily heat flows through a material. This measurement is dependent on the material's thickness, which means the number is not the same when it comes to the thickness. It is dependent on thickness. When we compare thermal conductivity in context to insulation, the lower the number, the better. The thermal conductivity of a material is used to calculate its R value. Now, what is the R value? Firstly, it's measured in meter square Kelvin per watt. The R value is the measure of a material's resistance to heat flow at a specific thickness. The higher the resistance a material has to heat flow, the higher the number. So how do we calculate a material's R value? We divide the thickness of the material, which is measured in meters, by the thermal conductivity measured in watts per meter Kelvin. When we compare the R value in context to insulation, the higher the number, the better. For thermal conductivity, the lower the number, the better. And for thermal resistance, the higher the number, the better when it comes to insulation. So now we're gonna find out the values of thermal resistance for my insulators which I have chosen. So firstly, the thickness of felt is 0.001 meters. The felt which I chose is polystyrene fabric felt. And the thermal conductivity of felt is 0.040 watts per meter Kelvin. And the R value, which I calculated based on these values, is 0.025 meters square Kelvin per watt. The thickness of sawdust is also 0.001 meters. Thermal conductivity of sawdust is 0.120 watts per meter Kelvin. And the R value, which I calculated, is 0.008 meters square Kelvin per watt. The thickness of bubble wrap, which is a low density polyethylene, also known as LDPE, is 0.001 meters. The thermal conductivity of bubble wrap is 0.038 watts per meter Kelvin, and the R value is 0.030 meters square Kelvin per watt. Now, based on all this, let's come to my hypothesis. Firstly, my null hypothesis is that there is no significant difference in the effectiveness of felt, sawdust, and bubble wrap in reducing the rate of ice melting. My alternate hypothesis is that the thermal resistance and consequently the effectiveness in reducing the ice melting rate differ among sawdust, bubble wrap, and felt, with bubble wrap being the most effective insulator. There is at least one significant difference in the mean time taken by the ice cubes to reach 0 degrees across different insulators. So now let's come to my experimental setup. So I have the total number of setups. So let's come to my experimental setup. First of all, my experimental design is repeated measures, and the total number of setups I have is 1 control setup and 3 experimental setups into 3. So the materials which I've used are ice cubes, bubble wrap, felt, sawdust, a digital thermometer, insulated gloves, and an airtight plastic container with dividers. Now, why did I choose this container? Because this is considered to prevent heat transfer and control environmental conditions in a standardized setup to ensure reliability. Sealing ice prevents contamination, where contaminants would have otherwise behaved as confounding variables. And a couple of control conditions which I've kept in mind and implemented are like the ice blocks used were of same temperature. The temperature was negative 3.4 degrees Celsius, and they were also of same volume, 27 milliliters. The experiment was conducted in a room with constant temperature. The insulators used had the same thickness, 0.001 meters, and a controlled setup with no insulator was included to compare the effectiveness of the insulating materials. The shots of my experiment will be shown at the end of the video. So now let's come to the analysis of my data. My independent variable is the thermal resistance of the insulators, and my dependent variable is the time taken by each ice cube to reach the melting point. Now the inferential test which I have used is ANOVA. Now let's take a look at the background of ANOVA, what it is exactly. So what is ANOVA and why do we use it? ANOVA, analysis of variance, is a statistical method used to compare the means of 3 or more samples to determine if at least one of the sample means significantly differs from the others. This is particularly useful when testing the effects of different categories, in this case the types of insulators, on a continuous outcome, in this case the time it takes for the ice to melt. So now let's take a look at the breakdown of some of the key components in an ANOVA test. The first one is between group variability. This measures how much the means of different groups, in this case different insulators, vary from the overall mean. A larger variation suggests that the groups affect the outcome significantly. Within group variability, this measures the variation within each group. This indicates whether the differences within individual groups are large compared to the differences between groups. F statistic, this is the ratio of the between group variability to the within group variability. A higher F statistic suggests a significant effect of the categorical variable, which is in this case again type of insulator, on the dependent variable, which is the time taken by each ice cube to reach 0 degrees Celsius. P-value, This tells us whether the observed F statistic is unlikely enough under the null hypothesis, which states that there are no differences among the groups, to warrant rejection of the null hypothesis. So now let's come to the data which I have collected of the melting times for each type of insulator. So for sawdust, the first setup took 10.1 minutes, the second setup took 10.3 minutes, and the third setup took 10 minutes. For bubble wrap, the first setup took 11.4 minutes, the second one took 11.2 minutes, and the third one took 11 minutes. For felt, the first setup took 10.9 minutes, the second setup took 11 minutes, and the third setup took 10.7 minutes. And for my control setup, which had no insulator, the first one took 9 minutes, second one took 9.1 minutes, and the third one took 9.25 minutes. Here is the table which has stated basically all the information which I've gathered till now. So let's just take a look at that. And now results of the ANOVA calculation to determine if the differences in melting times among the different insulators are statistically significant. So my F statistic came out as 99.737 and my p-value came out as 1.12 times 10 to the power minus 6, which is really small. So now the interpretation of these results. In terms of F statistic, this is very high, indicating that the variation among the group means, which are the different insulators, is significantly greater than the variation within the groups, which means basically the same insulator in the different trials. This suggests a strong influence of insulation type on the melting time of ice. And now coming to my p-value. The p-value, as I said, is extremely small, far less than 0.05, which allows us to reject the null hypothesis that there is no difference in the means of melting times across the different insulators. The ANOVA results show that there is a statistically significant difference in the ice melting times for different insulators tested. This implies that the type of insulator affects the melting time of ice significantly, and therefore not all insulators perform equally in retaining the coldness of the ice. The experimental setup and the choice of insulators are important in determining how quickly the ice melts. So this analysis provides a strong basis for concluding that choosing the right insulator can significantly impact the effectiveness of thermal insulation in practical applications. Now, again, so there are a couple more components to the ANOVA test, so I'm just going to give a short background on that before I show you my calculated components, like from my test. So, firstly, the total sum of squares, also called SST. This measures the total variance in the independent variable, which in this case is melting time. This analysis provides a strong basis for concluding that choosing the right insulator can significantly impact the effectiveness of thermal insulation in practical applications. So before I show you my calculated components, I will give a short background on the components. So firstly, we're going to talk about the total sum of squares, which is also called SST. This measures the total variance in the dependent variable, which is the melting time, considering all groups together. It's calculated as the sum of the squared differences from the overall mean. Next, the sum of squares between groups, also known as SSB. This measures how much the group means deviate from the overall mean. It's calculated based on the square differences between each group's mean and the overall mean, weighted by the number of observations in each group. Next, we have the sum of squares within the groups, SSW. This captures the variance within each group. It's calculated as the sum of the square differences of each observation from its group mean. Next, we're going to talk about the degrees of freedom. So we have three parts in degrees of freedom. Firstly, we have total degrees of freedom, which is dF total. which is n minus 1, where n is the total number of observations. Next, we have between group degrees of freedom, df between, which is g minus 1, where g is the number of groups. Then we have within groups degrees of freedom, df within, which is n minus g, meaning number of observations minus number of groups. Now, how do we calculate it? So basically, mean squares between groups, MSB, and mean squares within groups, MSW. So we calculate MSB by dividing SSB by the degrees of freedom between. And we calculate MSW by dividing SSW by degrees of freedom within. Now let's come to my components, like the calculated components for the ANOVA test based on the data. So based on my data, the components. First, we have the total sum of squares SST, which came out to be 7.8723. This is the total variance in the melting times across all observations. Next, we have the sum of squares between groups, which is 7.6673. This is the variance accounted for by the difference among the means of the different insulators. Then we have SSW, which is 0.2050. This represents the variance within each group, indicating how much the observations within each group differ from their group mean. Now coming to the degrees of freedom, the total is 11, between groups degrees of freedom is 3, and within groups is 8. And the mean squares, based on my calculations, MSB came out to be 2.5558 and MSW came out to be 0.0256. Now, the interpretation of this data, the mean square between MSB is much larger than the mean square within, indicating significant differences between the groups. This is consistent with the earlier F statistic result, suggesting that the type of insulator significantly affects the melting time. The degrees of freedom reflect the number of groups and the total number of observations, helping to normalize the sum of squares during the calculation of mean squares. These components form the basis for the F statistic calculated earlier, confirming the significant effect of insulator type on the melting time of ice. This detailed breakdown explains how each part of the variance contributes to our understanding of the data. So basically, in simple terms, the hypothesis that we've adopted here is that the type of insulator affects how quickly the ice melts. This hypothesis was tested to see if different insulators, which is sawdust, bubble wrap, felt, and no insulator in the control group, have different effects on the time it takes for the ice to melt. From the ANOVA test, since the p-value was extremely small, much smaller than 0.05, we have strong evidence to reject the null hypothesis, which stated that there is no difference in the melting times among the different insulators. Therefore, we accept the alternate hypothesis, which suggests that the type of insulator does indeed make a significant difference in the melting time of the ice. This means that choosing the right insulator can greatly impact how effectively it keeps the ice from melting quickly. Now, how will I find which is the most effective insulator out of my 3 insulators? So, I have chosen a manual approach to determine which is the most effective one by calculating the average time taken for the ice to melt. So in the sawdust setup, the average time taken by the ice cubes to melt was 10.13 minutes. In the bubble wrap setup, it took 11.20 minutes. The average time is 11.20 minutes. In the felt setup, the average time was 10.87 minutes. And in the control group, which consisted of no insulator, it took 9.12 minutes, the average. So from these manual calculations, the bubble wrap has the highest average melting time at 11.20 minutes. This indicates that under the conditions of the experiment, the bubble wrap insulated better than the other materials, leading to a longer melting time. Therefore, we can state that the bubble wrap is the best insulator among the tested insulators because it took the longest time for the ice to melt, suggesting it has the best thermal resistance properties in this experimental setup. So this was a manual approach. We can actually use a test called post hoc test to determine this as well. But in this case, I have used the manual approach, but still I'm going to give a bit of background. So using the theoretical basis of Tukey's HSD, which is honestly significant difference, post hoc test, if we had computed it, we would consider differences between these averages. The significant threshold would have been determined by the Tukey critical value for the given degrees of freedom and number of comparisons, with bubble wrap having a distinctly higher average than all the other groups. It would likely show statistically significant differences from at least the control group and possibly others also, depending on the critical value. So based on all this data, what is my conclusion? From the ANOVA results calculated earlier, the p-value was extremely low as mentioned, 1.12 into 10 to the power minus 6, suggesting that the chance of accepting the null hypothesis, which stated that all insulators perform equally, is very, very low, almost zero. This indicates strong evidence that the types of insulators do affect the melting time of ice, leading us to reject the null hypothesis in favor of the alternate hypothesis, which stated that the different insulators have different levels of effectiveness. In other words, there is a very high chance, nearly certain, that the null hypothesis is rejected based on the statistical evidence provided by the ANOVA test.